Hi everybody, welcome to this year's FusionNet Teachers Day. Just to let you know that this meeting is being recorded, so if you don't want to be in the recording, please keep your cameras off and yourselves muted. I think there'll be people kind of joining us, but we'll make a start now. So just an outline of the session, we're going to have a few talks from different people. So Kate and myself are going to be giving kind of an intro to Fusion. Then we're going to have a video from the lead of the Fusion Centre for Doctoral Training, Prof. Howard Wilson, who's going to be talking about the state of fusion within the UK. And then Nick and Ella are going to talk a little bit about career opportunities. And finally, Catherine's going to talk about the nuclear masterclass to end this session. If anyone has any questions throughout, please do send them in the chat or use the raise hand function if you want to ask them directly. But to start off with, I'm going to hand it over to Dr. Kate Lancaster from the University of York, who's going to give us a bit of an intro to fusion.
Okay, hi everyone, and welcome to this session, which is aimed at teachers, obviously, school teachers, and just trying to increase the knowledge about fusion and how wonderful it is, and how your young folk that you teach can get into the game, and even you if you've got bored of teaching. So I'm going to give you a bit of an overview of fusion in and of itself and what it is, and then that will sort of naturally lead into the rest of the session. So I'm just going to share my screen. So can everyone see that? Yeah. Okay, great. So effectively what we're doing as fusion scientists is trying to build a star on Earth, right? So that sounds a bit of an odd thing to do, but actually, obviously, the real point of this is, can we build ourselves a miniature star that we can turn off and on for sort of clean energy in the future, or cleanish energy in the future, rather. And this brief talk is the story of how we might go about doing that. Oops. So we have an issue. This picture nicely captures the issue. I took this out of a hotel window when I was staying in Yokohama, which is the sort of wider diaspora of Tokyo. And Yokohama is a big city in and of itself, and it kind of connects up to Tokyo. So when you look out of the window, you just get this kind of infinite sea of lights and action. And it really highlights the issue here, which is that we're energy addicts, right? We are addicted to using energy. Population is still increasing, you know, may stabilize at around 10 billion. And we need energy to power the lives and homes of these people, and to sustain life on Earth. And if we continue to get our energy via conventional sources, the conventional sources like fossil fuels are tailing off eventually, or be harder to get at the very least. And there's going to be a kind of gap between what we want and what we actually have, unless we choose to plug the gap with something else. Okay. And we really, really need to do that fairly soon. Not only is there an energy crisis, also we've got climate change to take into account as well. And so the sooner we move into an era where we're not adding carbon dioxide into the atmosphere, is a good thing. Now, I will say this now, that the fusion I'm talking about is not going to help with that, right? Because this is a long-term project, but nonetheless, it will help us sustain a carbon-free future, which is, so it's worth pointing that out right now. It's renewables and conventional nuclear that will help us with that issue. So this all sounds like rather bad news for a Friday morning, so I do apologize. But the point is, people like us on this video call are trying really hard to develop fusion as a technology, or at least find ways of developing fusion energy to sustain our carbon-free future and have lots of abundant energy with our little miniature stars that we build on Earth. So supposing we went back to the drawing board and we were all engineers and scientists, and we think to ourselves, well, what would we do? What energy source should we be trying to replicate on Earth, right? So if we look out into our own dear universe that we can see here, there's lots of little bright points of light, which are stars burning away. And they're actually fusion reactors in the sky, deep within the center of those stars. Basically what's happening is fusion reactions, light atoms coming together to produce heavier atoms, and the release of energy, which you can see here as photons coming towards your eyes. And basically all the atoms that make up our bodies are the direct result of nuclear fusion, of forged it either in the center of stars or supernovae for the heavier elements, right? So fusion is so fundamental to life on Earth, simply that nothing would exist in the universe without fusion. And so it in and of itself is extremely important and fundamental for our lives. But wouldn't it be amazing if we could take what's happening in a star and recreate that on Earth? And that might sound like an extremely crazy thing to do. And it's really difficult, and you'll see that, but it's really worth it, because the kind of abundance of energy that you can get from these fusion reactions is culpable. So how do we do this? What do we do on Earth? How do we get the energy? So in a star, you're turning hydrogen into helium, and we want to do exactly the same thing on Earth, right? So we're going to take two types of fusion, two types of hydrogen, sorry. We're going to take deuterium and tritium, right? So these are isotopes of hydrogen. And deuterium is present in seawater in huge amounts. For every 6,000 hydrogens, there's one deuterium. So there's a vast array of deuterium in our oceans. However, tritium, on account of it being radioactive, has a half-life. So it doesn't hang around in nature very long. So for every 10 to the 17 hydrogens, there's one tritium. So it's not really naturally occurring in that sense. So we have to make tritium, and I'm going to come back to that. So you might be thinking to yourself, well, Kate, you fusion physicists are idiots basing an energy source on something that's not naturally occurring. But we can make it, is essentially the idea. So I'll come back to that and how we do that in a while. So deuterium and tritium, they're charged particles. We need to give them a whole bunch of energy to overcome what we call this Coulomb repulsion, right? It's kind of like trying to bring two light poles of a magnet together. But once we've done that, and we're talking sort of heating stuff to tens or hundreds of millions of degrees Kelvin, right? So this is pretty extreme, right? Once they've overcome this Coulomb repulsion, then what happens is the nuclear strong force takes over, which is highly attractive force, but only at nuclear range, so the sort of range of the nucleus. And once that happens, then you get some state created, which then decays into helium and the neutron. And the neutron carries away most of the kinetic energy of the interaction. Well, where does the energy come from? Well, if we take the masses of deuterium and tritium and add them together, give them the energy so that they form the reactant products, and then we add those masses together, you'll find that there is actually a mass loss between the first and the second situation. So we've got this world's most famous equation here, E equals mc squared, and it's an equation everybody knows and has heard of, but doesn't necessarily understand the significance. So this is energy equals mass times the speed of light squared. Now, Einstein said the speed of light was constant in whatever reference frame you're in. And so for our purposes here, c, which is the speed of light, is a constant, and so c squared is also a constant. C is a big number, 3 times 10 to the 8 meters per second, so c squared is a big number. So we take this little value of mass that we've lost in this interaction, times it by a huge number, we get a huge amount of energy, right? So E equals mc squared is critical for getting energy out of fusion, and indeed fission, actually. So copious amounts of energy. So let's come back to this tritium problem. So the neutron is really important here, because if we surround the reactor with lithium, the neutron can undergo nuclear reactions with lithium and produce tritium. So provided we can cover a sufficient surface area of the reactor, then we can get enough tritium out. I say that we can do that. We haven't done that yet. That's research that's currently going to go on the next step devices that we can talk about later in the session. The other thing that happens is because of this interaction, the lithium gets hot, and then we can heat water to make steam to drive turbines. So it's a depressingly Victorian back end to what is a sort of space age front end, but that's how we get the energy out of fusion. We are actually heating water to make steam to drive turbines. So we know how to do that. So that's sort of a given there. So it's a really efficient way of getting energy. And if you look at the chemical energy contained from burning, the chemical energy released from burning 40 tons of coal, it's effectively the same as the energy you get from fusion from half a bath full of seawater and the lithium contained in a laptop battery. Now, the lithium obviously leads to tritium, so that's why we talk about lithium. So that's a really small amount of fuel. So it's very, very efficient. You don't need very much fuel to make this work. Also, that half a bath full of seawater and a lithium in a laptop battery is basically one of your lifetime's energy needs taken care of. So it's an incredibly efficient thing, which is why scientists have spent many decades trying to make fusion work, because it really is kind of the holy grail of energy generation. So there are other advantages to fusion, not just kind of the copious amounts of energy. So if we think about how we get nuclear energy currently, it's through fission reactions. Now, I'm pro fission. I think, you know, it's a key way that we can move to a carbon-free future in the intermediate term. And it's something we know how to do already. But there are downsides to this. You're taking a big atom, fission in this case, you're taking a big atom and splitting it into smaller atoms. So it's kind of the opposite of what we're doing with fusion. And you do get long-lived radioactive waste produced. So we have to manage that because it will be a burden on future generations. So that's a kind of unfortunate downside. Also, the other thing is with fission, you have to keep the fuel rods present at all times, and you have to carefully moderate the reactions because they could easily run away. So it needs constant watching the pot. And if you don't watch the pot, then you get situations like Chernobyl, for example, which is an absolutely catastrophic meltdown of a reactor. But as you well know, there's very, 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 very few of these stories. You can count them on one hand, but there are many, many, many nuclear reactors. So as long as there aren't stupid human errors, which is what Chernobyl was, actually just massive human error, then actually it is very, very safe. But nonetheless, the possibility is there. Whereas fusion, it's very easy to make fusion not work, right? We've been doing that for the last many decades, right? So because the fuel is not present at all times, there's only a very, very small amount of fuel present, you can just turn a fusion reactor off. And so there is no possibility of a meltdown in fusion reactors. So it is inherently safe. Now, I'm not saying there's no radioactive waste. There is, right? In fusion, right? There are neutrons flying around all over the place. They're going to interact with the walls of your container, whatever your miniature star is in, and activate them, i.e. make them radioactive. But it isn't long-lived radioactive waste, so it won't be a burden on future generations. And last but not least, we don't get carbon emissions from it. So whilst it's not going to address the near-term problem of climate change and pollution, it will help us sustain a carbon-free future in the decades to come. So, you know, it's good to. Could I ask people to mute their microphones, please? Yeah, cool. Thank you. So now we know why we're doing it. How do we do it? This is the crux of the matter, right? So in order to make a star on Earth, we have to heat matter to something like 150 million degrees Kelvin. That's 10 times hotter than the center of the sun. The reason we do this is we don't want to hang around and wait for reactions to happen like you do in the sun, which take ages. So we need many more reactions to happen, which is why we have it much hotter. How do we then keep matter at 150 million degrees Kelvin together without touching it? That's the crux of it, because you need all the particles to interact with each other. So you need the stuff to stay together, right? the sun and stars do it very easily with their own gravitational fields, but we don't have a lab the size of the star on Earth, so we need to do something else. And actually, what's really interesting is when you add energy to conventional matter, you know, you've got solids, liquids, and gases. Eventually, the electrons that are kind of whizzing around the nucleus part company. They gain enough energy that they can part company with the nucleus, and you get a soup of charged particles, the electrons and the ions, which are the nucleus once the electrons have parted company, all swilling around. And that soup of charged particles is called plasma. Hence why I'm sitting in the York Plasma Institute here. I'm a plasma physicist, because we need to understand plasma in order to make fusion work. And plasma indeed makes up 99.99999% of the visible universe. Obviously, that's the visible universe. The rest is dark matter and dark energy, which we're not worried about right now. So we're pretty lucky to be solids, liquids, and gases, because most of the universe that we know and love that we can see is made up of plasma. And we need to master plasma in order to master fusion. So there are three knobs you can twiddle to make fusion work, right? So the first one is temperature. But because we've got this Coulomb barrier that I was talking about that you have to overcome, temperature has to be pretty high. So temperature is kind of non-negotiable. So there are really two other knobs that you can twiddle, right? So the confinement time, as in how long you can keep the particles, or rather what we would refer to as the energy confinement time, is how long you can keep the particles together for where they're producing net energy. Because if you can keep the particles together and they're not producing net energy, well, that's pointless, right? So it's net energy is important here, right? And then the density of particles that you're trying to keep together. So you can see clearly here, there's sort of two approaches that you could keep a moderate density of particles or a low density of particles together for a very long time, or you can keep a very high density of particles together for a very short time, but then just do it over and over again. And that kind of represents the two main ways of actually getting fusion to work. So, so when I say the box, is like what are the approaches to fusion and what do we contain our star within, right? So the two kind of approaches that I'm going to talk about are inertial confinement fusion and magnetic confinement fusion. And they largely fall into the two camps that I was just talking about, which is moderate density particles for a long time and a very high density of particles for a short time. So first of all, we can talk about magnetic confinement fusion. And this is actually a picture of a reactor, a scientific device called JET that's on in the UK at Culham. And so we have a person from Culham to talk to us later, Nick. And this device, JET, is one of the most successful devices in the world. And the way it works is it's essentially a magnetic bottle. Basically, charged particles love following magnetic field lines. So if we can make a specially shaped magnetic field set of magnetic field lines that mean that the particles are kind of constrained to the middle of what is a donut-shaped device without touching the walls, which is game over. You don't want them to do that. So effectively what this does is levitate some hot plasma in the middle of a donut-shaped device. And yeah, JET is one of the most successful devices. So you will hear a little bit about that later. And this is keeping a moderate density of particles together for a long time. That's the approach of magnetic confinement fusion. On the other side, we have something called inertial confinement fusion, where you take a tiny little pellet of your deuterium tritium, take about 200 of the world's most powerful lasers, compress the hell out of this tiny little pellet until it's very, very dense, and then burn enough fuel whilst it's collapsed in on itself before it starts expanding again, burn enough fuel to get net energy, and then you do that at 10 hertz. All right, so it's kind of like a fusion powered diesel engine in that sense, right? So you can press and do it over and over again. And the device that you can see here is called the National Ignition Facility, which some of you may have heard about in the press recently. It's got some very exciting results out of this device. In fact, inertial confinement fusion is the area of fusion that I work in, because who doesn't love giant lasers, right? And so this approach here is the very, very high density of particles for a very short period of time. Okay. So supposing we get either of those ways to work, or a myriad of other ways that exist that are variations on the theme that I've talked to you about here, how would the energy come out? Well, so this is based on the Tokamak, but it can easily be the laser device as well. So we've got our plasma in the center here, and that's doing the producing lots of neutrons, and the neutrons come out into the surrounding area, which is surrounded with tritium. And the tritium is surrounded with lithium, and the lithium captures the neutrons to make tritium, but it also heats water to make steam to drive turbines. Now, this is, of course, what we call neutronic fusion, in that it is fundamental. We need neutrons for that to work. Neutrons do cause problems with materials because neutrons can fly out, they can activate materials, make them radioactive, but also you can get embrittlement of materials as well, which Nika will talk about shortly, and that causes issues. So ideally, we would want to move to a situation where we were doing what we call aneutronic fusion, which is where we don't produce neutrons. That's a hard ask. We haven't got to that stage yet, but if we did, we would have to think of ways of capturing the energy out that don't rely on neutrons. So, for example, if there are charged particles present, passing them through a coil, for example, to induce a current, for example. So there are other ways and means, but at this point, neutronic fusion is the way forward because the back end of it is something we know well how to do. And also it's the easiest one to get going in terms of conditions. So we're in a really interesting period of time at the moment. The landscape of fusion is absolutely fascinating because we've got these big major projects that are sort of, you know, science projects of many countries come together to do. But there are also private fusion ventures as well, where fusion is smaller as well. So that wasn't a thing less than 5 years ago. They were just starting. The credibility of these companies has increased very, very much over the last few years. And so not only have we got these kind of big scale projects, we've also got small fusion projects as well. So there's lots of really interesting stuff happening, both in the UK and also around the world in terms of varying scales of fusion. The next step device, which we call ITER, is going to be built in 2025, and Nika is going to talk to you a little bit about that. This is obviously very focused on magnetic confinement fusion, but also inertial confinement fusion is ticking over in the background as well, and has recently got some really exciting results, which I don't have time to talk to you about, but nonetheless, you know, the timescales for this are long, unfortunately. Even if we have got the physics to work, or nearly to work, realizing a science project and realizing an actual physical reactor are two different asks, I think. So we're in a really interesting time where it's kind of baton passing from science projects to industry driven projects for commercial gain, let's say. And so we do need a new generation of engineers and scientists that are well versed in not only science projects, but you know, the commercial world as well. So because this is where it's going to go, obviously, in the future. So on that note, I'm going to stop talking, and I'm going to immediately hand over to Nika, because we'll have some questions after the two talks and a brief video. Okay, so on that front, I'm going to stop sharing. So
fabulous, thanks, Kate. Yeah, as Kate said, I'm going to be doing the part 2. Hopefully everyone can see the screen. Great. So yeah, hi everyone. I'm Anika, and I'm based at the University of Manchester. And I'm going to give a little intro to materials for nuclear fusion. So just to start with, hopefully my slides will move. Great. So as Kate mentioned, the fusion reaction on Earth, the most efficient one for commercial energy production, is the reaction between deuterium and tritium. And that's just because it's more likely to happen. It's 100 times more likely to happen than other fusion reactions within a similar energy range. And this reaction results in the production of helium and very high energy neutrons. So 14 MeV neutrons are produced from this reaction, and I'll talk a little bit about those later on. As Kate mentioned, the next kind of big fusion project that's currently being built in the south of France is the ITER project. So this is going to be that donut-shaped device that Kate mentioned, a tokamak. And this is a massive collaboration between 7 members. So the EU, America, Korea, China, Japan, the US, and Russia. Hopefully I got that right. So all of those countries working together, plus people from other countries as kind of contractors are working there as well, producing this tokamak, and hopefully the plan is they will have their first plasma in 2025. As Kate mentioned, and just kind of for terms of scale of the reactor, there's a little person in the bottom right hand corner there, so it's around 30 meters tall and 30 meters wide, and then that's just the reactor. The whole site itself is massive, so a really huge materials and engineering challenge, just in terms of scale in itself. So what are the materials issues for fusion reactors? So I'm just going to summarize a few of them here and then go into a little bit more detail. So as I mentioned before, we have 14 MeV neutrons produced from that deuterium and tritium reaction, and they will interact with the materials that we use. We also have extremely high heat loads. As Kate mentioned, in the center of the reactor, it's going to be like 10 times hotter than the sun, around 100 million degrees. Hopefully we won't have those temperatures at the wall of the reactor, but we're still going to have extreme temperatures to deal with. Additionally, as a fusion community, we've chosen to use materials that will not become active or will have low levels of activation from those neutrons produced. And that kind of limits what materials we can use. As I mentioned before, you have helium produced from the DT reaction, and that also interacts with your materials. As does the general kind of plasma, that ionized gas in the center or in the reactor itself. What are the interactions between that and the materials? And then finally, I'm working in magnetic confinement fusion. I know Kate has mentioned inertial confinement fusion as well, but generating those magnetic fields and interaction of those magnetic fields is also something that we need to think about. So I'll go into all of these in a little bit more detail now. So if we start off with the 14 MeV neutrons, these neutrons will hit your material and kind of cascade through the material, kind of like when you hit a snooker ball and you get these kind of snooker ball effects hitting other atoms and generating defects. And then those defects kind of, both at the atomic scale and very, very short time scales, then kind of manifest themselves as engineering size defects as we increase it in time and length scale. And as fusion researchers, fusion engineers, this is really challenging to try and predict what kind of damage we're going to get, because we don't have these 14 MeV neutrons being produced. We're still building reactors, that are going to run with this DT. I know JET has just done a DT run, but for those timescales, predicting what's going to happen is a big challenge. So a lot of the time we're using ions or protons or fission neutrons to try and predict what damage we would get in fusion relevant materials and kind of extrapolate to the length and time scales for a fully functioning fusion reactor. So a huge challenge going from that small scale to large scale and extrapolating up at the moment is one area of research that fusion scientists are working on. Then if I move on to the heat loads, so this slide always is mind-blowing to me, just kind of putting in perspective the kind of temperatures or heat loads that we're talking about in a fusion reactor. So, you've got a Rolls-Royce Trent on the left-hand side, a re-entry vehicle, and then the ITER reactor, the steady state operations. This is a component called the diverter, which is kind of an exhaust for the reactor. That's already, during normal operations, going to be exposed to similar or higher heat loads than a re-entry vehicle going through the Earth's atmosphere, which is just wild and very, very challenging to deal with. And there's also these things called transients, which are kind of like instabilities in the plasma. So when that happens, you're talking about heat loads greater than welding, greater than a rocket even. So huge challenge. So finding materials that can deal with those temperatures is very, very difficult. For this diverter component at the moment, ITER is using tungsten-based materials. Then I talked about reduced activation. So this kind of periodic table shows how long it would take for certain elements to reach low-level waste criteria after 14 years of operation of a demonstration reactor in the first war region. And as you can see, we're severely limited in what materials we can choose. So we want to stick to the kind of light blue ideally, but there's no light blue up there. But even using, the gray materials is quite difficult to find materials that won't produce high level, radioactive waste. That's just in one area of the reactor. It varies depending on the areas we look at. So you can see here in the blanket region, so that's the area kind of on the first wall region of the reactor. There's a few more options available in terms of what materials we can go for, but it's really important that we choose stuff that doesn't result in high level radioactive waste. And then I mentioned previously that we have helium produced from the fusion reaction, so that's going to be floating around in the plasma, and the effect of the helium exposure varies with temperature. It varies with the kind of fluxes and fluences that we're talking about, and there's some really crazy effects that you might see. So for example, for tungsten, which is shown here, at kind of 600 to 700 Kelvin, the helium might result in some nanobubbles in your material. 900 to 1900 Kelvin, you get this really wild effect called fuzz, which is like a nanostructure that develops on your surface, which sounds pretty bad because, you know, we don't want that to erode and influence the plasma performance. But actually what's really interesting, one man's trash is another man's treasure. There's been research into this in other industries at the moment, because this fuzz is completely black, so it's a black metal, so it's got potential applications for semiconductors, and maybe even solar panels as well, so it could be really interesting. And then at even high temperatures you can get these kind of voids forming, and these can all influence your thermal properties, your mechanical properties, fuel retention as well. So we're talking about tritium. We don't want that stuck in the materials that we're using, because you know, we've got safety limits that we have to stick to in terms of how much tritium you can keep on site. I believe for ITER it's around 1 kilo they're allowed on the site at any one time. So you don't want to be wasting that stuck in your material, not being able to remove it. Then just more general kind of plasma material interaction issues. You can have this erosion, deposition, dust formation, fuel retention, as I mentioned, bubbles, blisters, embrittlement. So really challenging to work with this. We do have a lot of research on existing tokamaks who analyze the materials kind of post-mortem. They extract them from the tokamaks and look and see how they're behaving. But also internationally, we have a lot of linear plasma devices, which are basically like giant plasma guns. They're very, very cool. And they fire this plasma at kind of test components, test materials to see how they respond with the plasma and how they would perform in a reactor. So huge challenge again, but very interesting. And then I mentioned the magnetic fields. So we're generating around 13 Teslas in ITER, which is massive. If you compare that to a PET scanner in a hospital, which is only 1.5 Tesla. So developing the materials required to generate that strong enough magnetic field is a huge challenge. ITER is going to be using supercooled, superconducting magnets to achieve this. But there's also a huge amount of work on high temperature superconducting magnets, which is being studied at the moment. And I know a lot of the companies are investigating this, and that might potentially allow us to kind of build smaller reactors as well, which would be fantastic. But also, we're not only interested in how to generate those magnetic fields, but what is the impact of those magnetic fields on the materials themselves that we're using in the reactor. So that's another thing that people are looking at. My final slide is just going to show the kind of a schematic of the ITER tokamak and what materials that we're using. So we're going to have a stainless steel cryostat, which is like a fridge that holds everything in, and also a stainless steel vacuum vessel. As I mentioned before, this area here, the diverter is going to be made from tungsten, because that's got those, it's got the highest melting point of any metal and can withstand those high heat loads as well, although it's very challenging to kind of work with and manufacture. They intend to use a beryllium blanket here because that works quite well. It's quite plasma compatible. Although for future fusion reactors, because beryllium's again quite a challenge to work with and quite toxic, there's ideas to use either tungsten or other materials instead of beryllium in the blanket region. And then for the magnets, the ITER is using niobium tin or niobium titanium magnets. And I just want to point out that those magnets are super cooled. So that's almost absolute zero around here. And then in the center of your plasma, you've got around 100 million degrees Celsius, and nowhere else in the universe you have such a steep kind of temperature gradient going from almost absolute zero to 100 million degrees. And I think that just summarizes the huge challenge we have as material scientists and engineers in developing materials for such an extreme environment. So that's my final slide. I'm going to stop sharing there about material challenges. So now I'd like to invite any questions for myself or for Kate. So if anyone has any, either raise your hand or you can send them through in the chat as well if you don't want to ask them directly, if anyone has any general fusion questions. Anything from anyone? If not, then I'm going to move on to the next part of today's event, which is a video from Prof. Howard Wilson, who's the lead of the Fusion Centre for Doctoral Training in the UK. And that's going to kind of cover the status of fusion within the UK specifically. So we'll have that. And then if anyone thinks of any questions, please post them in the chat as you think of them.
Hello, my name is Howard Wilson and I am Professor of Plasma Physics at the University of York and have recently returned from a secondment to UK Atomic Energy Authority, where my roles included the Interim Director of the £222 million STEP Fusion Reactor Design Programme. I am going to tell you a bit more about the status of fusion, focusing in particular on the Tokamak. This is a fusion energy device which holds the hot fusion fuel in plasma state, keeping it away from the walls by a toroidal configuration of magnetic field. The international fusion community is presently constructing the ITER Tokamak in the south of France, which is the biggest international science project on Earth. Designed to deliver 10 times more fusion power than the power injected into the plasma to reach fusion conditions, it will answer the remaining science questions and address much of the technology required to build the first demonstration power plant. This is an exciting prospect that is at the culmination of decades of research. The progress to ITER can be illustrated with this figure. Along the x-axis, we plot the temperature. The centre of the sun is here at 10 million Kelvin. Up the y-axis, we plot the triple product, the product of the plasma density, its temperature, and something called the confinement time, which measures how good the magnetic field is at containing the plasma. The curves labelled Q equals 1, which is where fusion power equals the plasma heating power injected, and ignition, indicate the values of temperature and triple products required for commercially viable fusion power plants. Our story begins with the small Russian tokamak T3 back in the 1960s. A team of British scientists travelled to Moscow to make the first measurements of temperature in a tokamak plasma using a new laser-based system called Thomson scattering. These measurements showed the huge potential of the tokamak, but T3 was still a factor of 100 too low in temperature and a factor of 10,000 off in triple product compared to where a commercial fusion reactor must operate. Nevertheless, excitement about the very high temperatures achieved led a number of tokamaks to be built outside the Soviet Union during the 1970s and 80s, achieving still higher plasma temperatures and higher triple product. These acronyms are the names of different tokamaks. You can see how rapid progress was made through the 1980s, especially with the operation of the European tokamak JET in the UK, which is still the world's most advanced fusion facility. During the 1990s, both JET and the Japanese tokamak JT60U finally demonstrated that Q equals 1, scientific break-even, is possible. To go further with this kind of tokamak design required a still bigger device to achieve the necessary triple product, and that led to the design and construction of ITER. JET underwent a huge programme of work to replace all its internal tiles to be of the same materials as planned for ITER, beryllium and tungsten. This was all done with state-of-the-art robotic systems, again a key fusion technology. If ITER is successful, and there is much scientific evidence to indicate that it will be, we will need to push on towards the design of the first demonstration fusion power plant. Several countries are thinking seriously about this. In Europe, the focus is on a demonstration power plant that is a scaled-up version of ITER. The strategy is to build an irradiation facility called IFMIF-DONERS that will test materials in a fusion neutron environment and will operate alongside ITER and, in parallel, design the demonstration power plant called DEMO that will likely operate from the 2060s. The UK is a strong partner in this European programme, but with the urgency of climate change, is asking the question, can we deliver fusion faster and with lower capital cost? This is the goal of the STEP programme, the spherical tokamak for energy production. Specifically, STEP is assessing the feasibility of delivering a prototype commercial reactor by 2040 that is capable of providing net electricity, aiming to deliver an initial design by 2024. The spherical tokamak is a variant of the tokamak design that is more compact and can support a much higher plasma pressure for a given magnetic field. It is, however, a relatively new concept and does not have the huge plasma database that we saw earlier for the conventional ITER-like tokamak. A key input to the STEP programme, therefore, is not only to learn from our participation with Europe in ITER and IFMIF donors, but also to perform experiments on a new spherical tokamak called Mast Upgrade that is just starting to operate here in the UK. Together with advanced computer simulations and theory, and the US sister spherical tokamak NSTX Upgrade that will also operate in the next few years, this will provide the scientific basis for a decision on an accelerated fusion programme via STEP.
Fantastic. Thanks for that video. That was really interesting. I'd like to take a quick little stop now. I've been asked by FuseNet if we don't mind taking a screenshot of all the participants. So if you're happy to have a screenshot taken, could you turn your cameras on just to smile for 30 seconds? If you don't want to be in it, please keep yourself off camera. And also, if you don't want your name in there, please just send a message in the chat to either Catherine or myself, or just a general one if you don't want to have your name displayed at all. I assume this is everyone who's happy to have their photo in the screenshot. So I'll take it 1 second. Let me find there we go, my print screen button. If anyone wants to smile, pose, up. Yeah, wave. Why not wave? Oh, we've got one more turning on. Fantastic. Perfect. So if I just say, if everyone's ready, 3, 2, 1. Hopefully that's great. Sorry for that embarrassing pause, but anyway, if anyone has any questions, please feel free to keep sending them in the chat. Our next person who's going to be talking is one of our brilliant PhD students, Ella Fox-Widows, who's based at the University of Liverpool, and she's going to be talking about careers opportunities in fusion related to a podcast she's running called Fusion Focus. So over to you, Ella.
Thank you, Nika. Can you hear me okay? So hi everyone, my name is Ella Fox-Widows. I'm a PhD student on the UK Fusion CDT programme at the University of Liverpool. And I'm also a member of the FuseNet Student Council. So I'm just going to share a few slides with information about the different career opportunities in fusion, both in academia and in industry, and talk about possible career paths. So I'm just going to share my... Oh. Can you see my slides okay? Not letting me move forward or back, but oh, there we go. Okay, so to begin, the field of fusion is very interdisciplinary, and there are many overlapping topics that contribute to the field, including electromagnetism, fluid dynamics, material science, and so there are many different starting points to approach learning more about fusion. So for example, I studied an undergraduate degree at the University of York in maths and physics, and chose an optional module in plasma physics in my third year, and I actually went on to choose a plasma physics of fusion energy module in my final year. But I also know that there are a lot of people working and studying fusion who started studying different sciences or material science, nuclear engineering, other engineering disciplines, as well as taking a social science route, focusing on regulation or policy or science communication, which are all really important for the growing fusion field. To pursue higher education in fusion, there are many options in the UK and also in Europe and abroad. It's not very common for undergrads studying physics to specifically study plasma physics or fusion energy, at least in the UK, in detail unless there's a specific departmental focus, like there was at York where I did my undergrad. However, most STEM degrees cover a lot of the basics of fusion, like I mentioned, electromagnetism, atomic and molecular physics, nuclear physics, and so postgrad courses in fusion are accessible even without specific exam grades in fusion modules. So on this slide you can see a few different examples of the different postgrad courses in fusion, including the University of York's MSc in fusion energy, there's the UK Fusion CNC programme and the Erasmus Fusion EP. Within academia there are also some opportunities to go on for a PhD like the UK Fusion CNC programme, postdocs, fellowship, research positions, lectureships, both in universities and in national public labs like BCFE, the Cullen Centre for Fusion Energy in Oxford. And FuseNet also advertises opportunities for this kind of positions, for studying abroad, internships, grad roles, as well as summer schools and courses. there are many opportunities, not just in academia and public research, but also there are a large number of private fusion companies who are focusing on the kind of commercialization of fusion energy. The increase in the number of these private companies with the rapid growth of investment into fusion over the last few years, over the last decade, is going to result in more jobs popping up as well. So it's a really exciting time to get into fusion. And as the technology develops further, there will be an increase in demand for people joining the field. The Fusion Industry Association, which you can see the logo of here, is a non-profit association which supports the international fusion industry. And it's comprised of quite a few members now. As you can see, a few of the logos here, it's just kind of a fraction of their members. And they also have a strong outreach and communications program, including the Fusion News YouTube channel. So if you want to find out more about the latest Fusion news, you can find that on YouTube. So outside of Fusion, there are also a lot of career options available to people who have experience in fusion science. You gain quite a lot of transferable skills when studying a subject like fusion, and so academia and industry are not the only two options. There are a few case studies you can see on the website, on the Fusion GDT website, of where our alumni have gone on to be, and many graduates from the CDT have gone on to work in fields like finance and policy, consultancy, to name just a few. And so studying for a master's or PhD specifically in fusion doesn't confine you to only work in fusion after you graduate. You don't have to commit to a lifelong career in fusion if you're just interested in studying postgraduate. And so pursuing higher education in fusion also might show, like for me, that you're passionate about the environment and clean energy. So you could also choose to pursue a career in green energy and climate research. So I think the experience is very applicable to a lot of fields. As well as the opportunities mentioned in the previous slides, the fusion field is at a very exciting stage. Kate mentioned some really exciting results from NIF recently, and there have been a lot of really interesting developments and results over the last few years, and predicted to be a lot more coming with ITER. So the field will continue to grow. And so with that, the number of opportunities available for students joining the field will increase with this. The UK have just announced, for example, the STEP programme, the Spherical Tokamak for energy production, and ITER is kind of currently under construction in the south of France and has some exciting results coming hopefully in the next few years, 5 to 10 years, 2025, I'd keep a lookout. And alongside these projects, the private industry is also growing quite steadily, with many companies saying that they're aiming to achieve energy break-even and build demonstration fusion power plants on smaller timescales than ITER, STEP and demo. So it is really an exciting time to join the field. So now for a quick shameless plug, I wanted to let you a little bit know about the podcast that I started recently. The podcast is called Fusion Focused, and the aim of this is to chat with specialists in fusion and highlight the range of roles and careers that are available in the field, and the different paths that my guests took to be where they are now. So it's presented in an informal, kind of chatty, conversational style, and it's aimed at people interested in fusion and the fusion field. But you don't need to have a background in fusion to follow it. Hopefully, you know, some of your students might find it interesting. And there are currently 5 episodes released, with new episodes every other Monday. So it's available on your usual podcast site. So yeah. And any questions?
I have a quick question.
Yeah.
What inspired you to begin that podcast?
Oh, thank you for your question. So I did a little bit of outreach and communications work with the Fusion Industry Association, and I enjoyed the kind of podcasting side of it. I like talking to people, and I like fusion, and I'm quite passionate about fusion. So I wanted to kind of set up a little project where I could talk to other inspiring experts in the field and kind of showcase them. There isn't really a podcast like that that's kind of more bios about cool people in fusion. So I wanted to show that there are different routes into fusion and show that the reasons why people are so passionate about fusion. And that was my main motivation.
Oh, great idea.
Thank you. And also Anika and Kate, who are in this call, there's episodes with them as well, so listen to them.
Fantastic, thanks Ella. Do we have any more questions for Ella? And yeah, definitely do check out the podcast. It's a really great resource, I'd say. I've listened to a few of the episodes myself, and I just think it's a great way to just be aware of what opportunities are out there for teachers and for students alike. I think it's fantastic. So thank you, Ella, for your talk, and yeah, for that amazing podcast that you're running.
Thank you. I also wanted to mention that the Fusion focus that I ran is kind of focused on the bios of people in Fusion, but there are a few CDT members that also set up the Glass of Seawater podcast, which you can find on most podcast sites. And that kind of goes into different research and kind of outlines Fusion in a more scientific way. So there's kind of two sides, the scientific way and then the kind of people aspect that you can find on most podcast sites.
Fantastic. Thanks, Ella. Our next talk is going to be coming from Nick Muldahl from the UK Atomic Energy Authority. So he's going to talk about how do you get into those careers in fusion, so about the apprenticeships and opportunities available at UKAEA. So I will pass it over to Nick.
Cool, thanks very much, Nika. Great to be here. So just let me get my screen share slides up. And while I do that, I'll just say I'm definitely going to be checking out Fusion Focused. Sounds awesome. And the Glass of Seawater I have listened to before, and that is also very good. So highly recommend. Can I just check that you guys can see the screen? Yeah, excellent. So as Nika said, I'm just going to kind of do the second part of our careers in Fusion bit this morning, and focusing more on how or routes that you might go into a career in Fusion. But just stealing a couple of slides from Ella just gone, a little bit of a recap to just show that actually there are so many different things going on in Fusion. Lots of different fields that you can get into, but also lots of different organizations. So we've got all the private companies, and then you've got all of the publicly funded organizations that are doing work in Fusion, and the wider nuclear sector too. So it really is lots going on and lots of opportunities for lots of different people. Myself, I actually don't have a physics or an engineering background. I did a biology degree and came into science communication through my love of outreach and doing some ambassador work at university. And hopefully we'll be able to tell you some of the other non-technical things that people can get involved with in Fusion as well, because we're really passionate about trying to open this up to as many different people as we can. So traditional route to get into Fusion is probably expecting to go down the sort of physics and engineering route, and it all starts at school. So students may well want to go and study physics, maths, and those kinds of typical sciences, and then go on to a university degree, where again they might further follow a degree in either physics. As we've already found out, there's plenty of courses out there that do specialist modules in Fusion towards the sort of final years of the physics degrees, but also there's lots of different engineering degrees that are very applicable to various aspects of Fusion at the moment. And I think Fusion is very much moving towards greater number of engineers coming into the field as well, because we've had a lot of understanding about the physics over the last few decades, and now as we're building the full-scale prototype reactors and looking at more of the design efforts with ITER and demo, lots of different engineering skills are really going to be key to pushing forward onto getting onto the grid. But there are other routes as well in terms of typical subjects you might go down. There's plenty of people that work at where I am, UKAEA, doing maths and using their maths degrees in lots of modelling. There's also a lot of computer software people as well, lots of developers. But then there's also various chemical sciences, material sciences, a big growth area too. And I know there's a growing number of sort of environmental science degrees going out there as well. We're getting various people from lots of different sort of subject-based backgrounds into the field now, which is really exciting to be broadening it up. But that kind of gets you through the education cycle. How do you then go on and work into all of this stuff? Well, I've already heard about some of the academic pathways where you can go on to do a PhD or a master's and follow the more sort of academic route. But there are also direct employment routes, for example, through graduate schemes. At UKAEA, we run a really healthy graduate scheme where we've just a couple of weeks ago had our new cohort of 50 graduates start. So we really are growing quite a lot. And then even within those graduates, they come from lots of different disciplines. We've got physicists, we've got engineers, we've got chemists, all sorts of different routes. And a lot of the graduates that come and work for us do also stay on, which is really nice. A couple of them go on to work for other fusion companies too, and others go on to other industries, like you heard from Ella, being a lot of them going down the sort of green energy routes, alternatives to fusion, looking at the sort of, I know we had a couple of people go into wind energy straight after our grad scheme as well. So look out, I would encourage you to kind of like promote among your students in the long term of graduate schemes alongside academic pathways. But there are there is a route to go to straight from school, and this is a growing area. I'm sure all of you here are aware of apprenticeships. I think any general engineering apprenticeships that there might be locally to where your students are based would be great routes to getting them lots of core engineering skills, and then that could easily lead on to a career in fusion if they then apply to somewhere that is focused more on fusion. At UKAEA, we really are keen on growing our apprenticeships as much as possible, to the extent that we now have this facility on our site called Oxford Advanced Skills, and this is effectively an apprentice training college on our site at Culham, and there we'll train our engineering apprentices for a couple of years before they then start doing rotational placements across the organisation. Level 3 engineering apprentices, sort of good for if you kind of just come out of GCSE or A-level routes. But they are also now offering degree apprenticeships too. So this is becoming increasingly popular with us, where some students still want to kind of get that experience of university degrees, but also want to be earning straight away for a variety of different reasons. And this allows them to have part of their time working at our organisation, and then a couple of days a week actually attending university lectures, either online or in person as well. And so there are plenty of opportunities to kind of get skills and get qualifications while going straight into the workforce for Fusion too. But alongside all of the sort of technical roles, we really are keen in promoting more business support apprenticeships. And actually, I think a lot of the things that you heard before about how the skills you get from studying fusion and working in fusion can be transferable to other areas. All of those special support areas are things we need within the fusion industry too. So we have plenty of apprentices at our organisation that work in like either our finance department, our communications team, our early careers and recruitment groups. All of these people are essential to making the wider fusion industry work as well, alongside all of those technical roles. So we really are after just anyone that would like to join us. If you want to know more specifically the UKAEA apprenticeship scheme and our early careers routes, head to our ccfe.ukaea.uk website, or you can just Google UKAEA early careers. That comes up in my search engines. So just a small little bit about UKAEA. A lot of this you will kind of like heard from other bits of this morning, which is sort of great to see how much fusion is featuring. We are the UK's leading national fusion lab. We're a public sector body, and we host and operate JET on behalf of all of the European scientific program that gets used for it. And then Mast Upgrade is our newer spherical tokamak design that's more compact, and actually one of the key things that Mast Upgrade is looking at is how we can deal with those high heat loads. You heard from Anika, and they're such a challenge, and we had a really, really exciting result back in June this year, where our new Mast Upgrade diverter system called the Super X diverter, because we like cool funky names in fusion, that shows that actually we can reduce the heat loads by 10 times just by using this different diverter configuration. So that's a really, really sort of key progress that we've had very recently. And then it leads on to all of the sort of future fusion experiments that we are also contributing to as UKAEA. We're contributing design effort and scientific effort towards ITER, and also developing all of the things that you've heard from Howard before and others about demo and our work into the STEP program as well, where both of those are trying to be full-scale prototype reactors, actually getting us energy onto the grid, and then those templates will be used by the big energy companies to really roll out fusion across the world. UK, you might not know, is actually now based across 2 sites. We've been at Culham Science Centre for several years, but very recently we have also got a new site at the South Yorkshire Advanced Manufacturing Centre. And at both of these sites, there's lots of other engineering and science companies going on. So a really nice kind of place to work in terms of lots of innovation going around. But going to focus a little bit on some of the facilities that we do at Culham, just to show you some examples of all of those different fields that people can really work in. So JET is our main one, and that is based at our Culham site. But we have all of these other facilities too. So STEP, this future design program, where we're needing lots of design engineers at the moment and a whole host of other people with different skills to take that future looking forward look. Mast upgrade, this is the other fusion device. Very similar skills that we're needing between JET and mast, but a lot of the sort of academic work that's done through the Fusion CDT program and other university links is contributing a lot towards mast upgrade. We've got a lot of academic links with that program. RACE is our remote applications in challenging environments facility, and this is looking at some really cool robotics and cybernetics work and how we can actually use robots to go inside challenging environments like a fusion machine at 150 million degrees and slightly radioactive, and how we can use remote handling techniques both to help us repair and upgrade fusion machines, but also apply that to other areas of the nuclear industry too. And then the last one that I kind of wanted to highlight is the MRF. This is our materials research facility. As the name would suggest, we're developing some cutting edge materials science at MRF, and it's kind of another user facility where universities, but also big industry can come and use the MRF to study mid-active radioactive samples. So one of the things that we're really keen at the moment as UK is to not just further all of our efforts to make fusion happen and on the grid, but actually really cement ourselves sort of society and industry benefit from all of the technology that we've developed for fusion and open it up to how it can be used in other areas too. And then the last one I was just going to point out on this map is that Oxfordshire Advanced Skills Centre that we've recently got, and that's really growing. And it's not just for UKAEA apprentices either. We have various other engineers coming to use that training college now, so it's becoming a really thriving part of the site. And just the last sort of bit that we wanted to end this section on was all of the things that actually people can be doing while they're at school, thinking about getting into recurring fusion. Fusion has a really big outreach section, and particularly at UK, where we can offer on-site and virtual visits to groups that want to come and experience stuff up front. And we offer our on-site ones mostly for A-level groups, and our virtual visits are available for any GCSE science groups, so do get in touch if you'd like to book one of those. UK and other departments at universities across the country go to festivals and other public events, so you'll almost certainly be able to find something nearby might have an appearance from Fusion. We've got a really good work experience program, which is mostly done admittedly by people within the sort of Oxfordshire or regions around the south for year 10 and 11 sort of GCSE students. And we've got a range of online resources that we sort of were constantly trying to develop, of which I think the most useful one we found is our Fusion tutorials series on YouTube, which we developed last summer. These are a series of sort of 20 to 30-minute little primers giving you some very basic bits about Fusion, and each one kind of builds on the next, and there's kind of 6 of them in the series that we've been finding are very popular with students and general interest adults as well. So if you're interested in any of these, get in touch with us at education.ukaea.uk. That's the best email to reach me and my colleagues in the outreach team here, and we can direct you to all of the different things that are going on. But there are also various university schemes that are running outreach programs, and that's what you're going to hear about just after me. But just before that, if anyone has any questions for me right now, more than happy to take them.
Fab, thank you, Nick. Does anyone have any questions for Nick in the chat? No? I think it's just really interesting as well, like from what Ella and Nick both have said and what Kate was saying before about the move from going from a scientific endeavour to a more industrial one. What a broad range of opportunities are out there. So yeah, I think that's really, really interesting. So thank you very much, Nick, and thank you, Ella, for that section. So as Nick mentioned, our next talk will be about kind of more outreach resources available from the University of York. So I'm going to pass it over to Catherine Leach to talk about the Nuclear Masterclass series that York is running.
Thanks so much, Anika. So I'm going to talk a little bit about the Nuclear Masterclass first of all, and then I'll just mention a couple of other ones in passing. Just before I start, just to introduce myself, so my name is Catherine Leach. I'm currently the outreach coordinator at the University of York, but I also coordinate the Fusion CDT, so that's the Centre for Doctoral Training, that runs across the 5 universities. So that's Manchester, York, Liverpool, Oxford, and which one have I just forgotten?
Durham.
Thank you, Durham. So we have a range of programmes that happen in person most of the time, obviously not for the last 18 months, which is why I'm going to talk a little more detail about our online programme with the masterclass in a second. Prior to doing the outreach, I was a physics teacher, so I've got that educational background, so I was a physics teacher for 9 years before moving into university outreach. So do feel free to jump in and ask questions as I go through this, and let me know if there's anything that we can help you with to support your students. So firstly, just to say, in terms of contacting me, we can be contacted at physics-bindingblocks@York. I've just posted that into the chat. And we have a big educational programme that runs around nuclear physics, which is where the Nuclear Masterclass sits. Now, this resource is largely pitched at sixth form students, so that's post 16, but it's also accessible to younger students who are particularly keen on this area. So the page that I'm showing at the moment, which again I will just post into the chat, is the registration page for teachers. So we just ask teachers to register just so that we've got a sense of who's using these resources. We promise we don't send all sorts of spam. We will literally contact you purely with an evaluation form, probably once a year, and also just to let you know if we're running a live version of the masterclass. So we've run 2 versions of the masterclass live, and I'll talk about those in a little more detail once I've just shown some of these teacher resources. So also on this page, as well as the sign up button, there's also some further information if you're a UK-based school that links to the exam different specifications. So feel free to have a look. Depending on your exam spec, it shows how the Nuclear Masterclass links into those different examination boards, including the IB as well, if you're teaching the IB. Once you're in, once you're registered, you'll get access to this site here. Which is our homepage for teachers and links you to all the resources. So we'll have a look at these resources and then I'll come back to this page and show you some of the bonuses for teachers like answer sheets. So if you click on the Masterclass homepage, this is what you can share with your students. And we have a series of modules that students can either work through the whole course, or they can dip in and out, pick particular elements of it, or you can just select out individual videos and things like that. So we have an introduction to nuclear physics, first of all. Then we start with a kind of building up the sixth form curriculum content, so around binding energy and decay chains. And then we move into some specific areas, so nuclear astrophysics, fusion, which obviously we're talking about more here, and medical physics at the end. So if I just look at the fusion module. So what you can see here is that each module has a list of the activities that are included, and then it goes through with a series of video content and activities, text-based information. So for example, there are question sections with PDF documents that can be downloaded and answered, videos, and also activities such as at the top here. So the fusion, we've got all about energy resources. So there's a series of various graphs and data that people can have a look at. This is the live energy mix of usage in the UK. And then there's a series of questions that goes with that data. In some of the other sections, we've got things like computer modeling. So using Excel to model radioactive decay, for example. We've got one modeling neutron stars. So you can actually use some data about neutron stars to work out what the smallest possible neutron star would be, and so on. So a mixture of different types of activity there. So just to return then to our teacher page, the bit that the teachers gain that's separate to this is that at the bottom here, we've put copies of all the worksheets in, so all of those different tasks, and you can see that there's answer sheets for all of those as well. So you can see for modelling activities, we've put copies of the spreadsheet in so that you can use the spreadsheet as well. This is a completely independent set of resources that you are welcome to use at any point. So you can just register, dip in and out, and use in any way that you choose. We also offer live versions of this specifically for students. So here is our one from summer 2020, where we would have a question forum on there, and it runs for about 4 weeks, with a couple of weeks at the end for students to be able to catch up. This includes live webinars, the question forum, as well as interactive versions of all of those questions. So you saw on the teacher version that we've got that it's PDF format. In this, it's all done with Google Forms, so that you can actually answer these questions, and we can then issue certificates. Now, it is also available to teachers, so that if as a teacher you would like your students to be able to work through that version and get a certificate at the end and complete everything, then you can just contact us at Physics-Binding Blocks, and we can set your students up onto one of those sites, and we'll monitor them through, and we can issue them with a certificate at the end of the course. Once you're registered for this, we'll also let you know when our next live one is, which we hope to be the summer of this year, so that will be another resource. So that's just a very whirlwind tour through the Nuclear Masterclass. If there are any questions on that specifically, please do give us a shout, and otherwise I will just mention one other resource. Okay, so the other resource I was just going to briefly mention, I obviously mentioned a couple of podcasts. The other one I was going to mention was our MOOC, Massive Open Online Course. Again, I'll just post this into the chat. So this is a Future Learn course that covers physics more broadly, but the reason I'm mentioning it here is that the first week is about plasma physics and fusion. And it includes the video that you saw earlier with Howard talking about the direction of travel for fusion. It's no longer a monitored course, which means that we don't have people answering questions live at the moment, but there will be future runs of this where you can ask questions and you can register for those on Future Learn's site. But at the moment, it's just open for you to be able to look through, or for your students to be able to look through and work through at your own pace. So for example, this first week, plasma physics and fusion, there's an introduction to the course. Kate, who you heard from earlier, is our lead educator. So you'll see lots of videos from her introducing the different weeks and the different content. There's then, again, information to have a look at and activities to have a go at as you work through. So that covers fusion in the first week and then moving into different aspects of physics in the following 2 weeks, which again, you're welcome to work through the whole content or dip in and out as you choose and just look at particular elements of that. So if there are any questions, please do ask, and if we can support in any way, please feel free to drop us an email to that physics-bindingblocks@york.ac.uk, and we'd be happy to support in any way we can.
Thanks, Catherine, for sharing those resources. And yeah, again, couldn't recommend them highly enough. They're really fantastic. And I've also seen in the chat that there's some good feedback on the UKAEA resources as well, which is fantastic. So that brings us to the end of our session. So unless anyone has any final questions, I'd like to thank you all for coming. I hope you found it useful. If you have any feedback or any questions that you'd like to ask afterwards, please do feel free to email or get in touch as well. But yeah, I hope it was useful. The next session I think is at 1:30, so you should, well, 1:30 UK time, obviously it depends where you are, because I know we've got people from everywhere, which is wonderful. So that will have separate kind of joining details and stuff like that, so you should hopefully all have that available. And yeah, thank you very much for joining, and hopefully see you all soon.
Thank you all.
Thanks. Bye.
Bye everyone, take care.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks.
Bye.